This presentation will teach you that SMeft, a popular theory among particle physicists working on the Higgs sector of the Standard Model, can be falsified even if new particles are not discovered, and how to do it employing the N-Higgs final state at the collider. It is to be presented at the 2022 April meeting of the APS in New York. It is meant for professionals, and I must warn you, gets rather technical. You have often heard that the Higgs discovery reveals the origin of mass, but that is an exaggeration. Most mass comes from the strong QCD interactions. The Higgs was postulated in trying to understand radiative beta decay, for which it succeeds, and also gives the tiny mass of elementary particles. Because the electron is one of them, however, and it controls the atomic radius, one thing that the Higgs does for you is to set the size of all objects. Come visit our department at Madrid sometimes. Now this talk is about the electroweak symmetry breaking sector of particle physics. In the Standard Model, and as much as we know, this is made of 4 particles, the Higgs we just talked about, and 3 Goldstone bosons, or if you want, longitudinal gauge bosons by the equivalence theorem. These are packed in the capital H doublet and make up the Standard Model Lagrangian, with the terms of the right, the usual Higgs potential. This Higgs potential is a goal of the LHC experimental program, and in the Standard Model has the shape of the green line over here. However, because experiment is advancing only slowly, it could be anywhere within the gray uncertainty band. We really only know it very near the physical vacuum at the minimum. Falsifying the Standard Model is easy. Go and discover new particles. In their absence, try discovering new forces among the known particles. For a few years now, we have known that there are not relevant new particles below about half or 1 TeV, so that there is a mass gap between the known W and H spectrum at the bottom and any new physics high gap. We are therefore in the second situation, looking for new interaction forces among the known particles. This scale separation lends itself to the exploitation of effective theories. The rest of the talk is dedicated to discussing them. They go by the name of SMeft, Standard Model Effective Field Theory, and HEFT, Higgs Effective Field Theory. So SMeft is an extension of the Standard Model where new interaction operators are added. Of interest for this talk are those that multiply the square derivative of h squared here on the right of this formula, that we bunch in one function b. The particle content is still organizing a Higgs doublet that transforms linearly under the Standard Model global symmetry. The Higgs boson always appears in this H plus V combination, which introduces more symmetry, more degeneracy if you want, among the Lagrangian coefficients. It naturally arises when the Higgs boson is taken as a fundamental particle, and operators are added according to their canonical dimension. The number of fields suppresses the order of the operator. Here are a few at canonical order 6. The 2 on the left, particularly the one at the bottom, are of immediate interest to us. These and many more operators are under intense scrutiny, and the coefficients, their size, is being constrained by LHC global fits. So far, all are compatible with 0. Finding any of them falsifies the Standard Model after all. The question that we address here is rather how do you falsify the Standard Model EFT framework itself in the absence of new particles? Is this theory final, or is there another wrap around it? That is precisely what the Higgs Effective Field Theory does for us. Its Lagrangian, here on the right, is written in terms of the Higgs and Goldstone particles, featuring a potential in the Flair function f that we are going to talk about. Note that this function multiplies the kinetic term for the Goldstone bosons, so it must start at 1 when h is equal to 0. After that, it yields couplings between the Goldstone and various numbers of Higgs fields. HEFT is the most general EFT expansion around our physical vacuum with the 4 particles, H and the Goldstones. It has less symmetry than SMeft, lacking the doublet structure. H is a singlet, and the W's an unrelated triplet. HEFT is the old electroweak chiral Lagrangian, but with an additional Higgs singlet. It is typical of composite Higgs models, in which the Higgs itself is a Goldstone boson with an as yet unknown symmetry group. For many purposes, you can think of HEFT as spherical coordinates and SMeft as Cartesian ones. There are cosmetic differences between both SMEFT and HEFT. While the first counts the canonical dimensions of fields and derivatives, the second counts the number of derivatives independently of how many particles there are. For example, the two diagrams on the left, both with two derivatives but different 4 and 6 numbers of particles, are of the same order in the HEFT counting, but not in SMEFT. The San Diego group, Alonso, Jenkins, Manohar, gave a beautiful clarification of how every SMEFT can be cast as an HEFT, but some HEFT theories are not SMEFT. The key is our Flair function here, which gives the radial scale of the electroweak symmetry breaking sector field space. The Goldstone bosons are the angular coordinates circulating here. HEFT is a Taylor expansion around the vacuum, H equals 0, the physical vacuum. But SMEFT is an expansion around the doublet field having 0 modulus, a symmetric point. We are pretty sure that our vacuum exists, but it remains to be seen whether the symmetric point that SMEFT and the standard model must have actually exists. Now the Higgs potential V of H is kind of low energy from the perspective of the electroweak symmetry breaking sector. The LHC is taking data over here, near the minimum, but if there is new physics in the few TeV region, with energies much larger than the mass, which is of the order of the potential, this potential will be quite small, up there, with the Flair function dominating interactions, because it is derivatively coupled. So why do we need a 0 of the Flair function? This is shown here. We need to transform these terms of the standard model EFT Lagrangian by substituting in them the H doublet into HEFT form. To do it, we need a canonical transformation, which is non-linear. Although the Higgs potential is unique, the fields assigned to it by SMeft and HEFT are different. There is no obstacle in integrating this relation, so that every SMeft can be cast as a HEFT. Nevertheless, the inverse operation is not guaranteed. The reason is in the screen's middle. The square modulus of the Higgs doublet is V plus H square, but its derivative square contains that square modulus on the right-hand side. That means that upon solving for the derivative square of little h, to invert, we need to divide by the modulus square here. This can cause a singularity around the modulus of the doublet being 0, but you cannot perform a Taylor expansion around the singular point. Thus, SMEFT, which is such a Taylor expansion around the symmetric point, here h equals 0, cannot be deployed. Now hang on, there's a way out. Make this whole factor to its left vanish. If it is 0, we're fine. SMeft exists because the 0 in the denominator is cancelled. So a part of the Higgs Effective Field Theory space, but not all, can be cast in SMeft form. We just need to make this 0. But wait, there is more to it. SMeft, even if a 0 of that quantity can be found, is still a Taylor expansion around the false vacuum at h equals minus v. It needs to converge far enough from that point to cover our own physical vacuum at 0, no Higgs particles. Vice versa, HEFT on the right plot can be extended all the way to the symmetric point, allowing to define SMEFT. But on the left, the convergence radius is too small, and we cannot reach the symmetric vacuum, thus no SMEFT. The problem is that, to decide, you need to know your function f of h very well, and we are only informed by experiment on a couple of the coefficients at best. To wrap up, SMEFT is deployable when that Flair function has a 0, the symmetric point, and when all its odd derivatives vanish at that symmetric point to have a chance of analyticity. The standard model has just such structure, since f vanishes, as does its first and all its odd derivatives at h equals minus v. The standard model is of course a particular case of standard model effective field theory. We can quickly look at the sensitivity of this Flair function to varying its coefficients. First, A1, the linear piece that couples two Goldstone bosons to one Higgs boson. Here is our vacuum, and any variation around a standard model green parabola that is conceivable by current bounds does not seem to spoil the symmetric point of the standard model at the bottom. Now, the story is different with two Higgs processes. Here one can conceivably vary the second coefficient and spoil the 0, and the same goes for higher coefficients. to measure them requires multi-Higgs final states. Next, when and because SMEFT is part of HEFT, it can be used to predict the parameters of the second theory, Higgs Effective Field Theory, in terms of CH box, the Wilson coefficient of one peculiar SMEFT operator that is often overlooked in analysis. We can eliminate this coefficient, because these equations are linear, and do it also at order 1 over lambda to the fourth with the next SMEFT operator, to obtain correlations among HEFT parameters that, if experimentally violated, would lead to the falsification of SMeft. This table shows the correlations that we have found for low-order coefficients. For example, if experiment shows that 4 Higgs bosons couple derivatively to 2 Goldstone bosons with much more than, say, 1/3 of the strength with which one Higgs exceeds the standard model coupling, then SMEFT is falsified. With current atlas bounds for A1, this would mean any value beyond -0.02 or 0.06. Now, higher order SMEFT operators weaken these correlations. But if HEFT's A4, say, exceeds the interval given here on the right, then SMEFT certainly ceases to make much sense. So how is this to be done? Well, proceed to high energy, isolate the process WW with longitudinal modes to n Higgses, and use these amplitudes that we can provide you with. Extract the HEFT coefficients, closely related to the kappa framework, if you know that, and test our correlations. By the way, at order 1 over lambda square, a cute prediction of SMeft is that the cross-section ratios of NH to NH are independent of the CH box parameter. We call this production of many Higgs bosons a flair, and thus the name of the F function as flair function. So n Higgs boson processes can access up to the nth coefficient, but thermodynamic properties are sensitive to the entire Hamiltonian at finite temperature, and thus to the entire flair function. Perhaps one day we will have hundreds of Higgs bosons in the final state, just like heavy ion collisions, after 60 years since the discovery of the pion, started producing hundreds of pions in each event. Meanwhile, we should point out that HEFT also has a potential V of H that is restricted if SMeft should be valid, for the same analyticity reasons. We are currently working on the correlations of the coefficients in the HEFT expansion of the Higgs potential V. Here they are. If one expands the Higgs potential within HEFT, we get at order 1 over lambda square these preliminary constraints that would also falsify SMeft. They have the advantage of not involving Goldstone bosons at all, so they can be tested with lower energy data without use of the equivalence principle. But they do require multi-Higgs boson final states. To conclude, the mass gap between the Higgs and any new particles yet to be found suggests that EFT is a method of choice. A popular one is SMEFT, that resembles the textbook standard model, but Higgs Effective Field Theory is more general. In this work, we propose to handle HEFT from within with experimental data and study its coefficients to try to falsify SMEFT, in the sense of Popper, and for this, we have presented new correlations within HEFT itself that must be satisfied if SMEFT is to be valid, both for the Flair function coupling Higgs and Goldstone bosons and for the Higgs potential itself. It remains to thank various European, Spanish and Italian authorities and institutes for their support of basic science.